Hey, welcome back. Now that we know the product rule and the quotient rule, it feels like we can take the derivative of any function. And we're close, but there's one major thing that we still can't do, and that is take the derivative of functions that are more complicated than your basic parent functions. Right now we can handle sine of x, we can handle cosine of x, x squared, x cubed, but what about when we take things up a level of complexity? What about 1 plus cosine x squared? What about sine of x squared plus e to the x? These are technically compositions of functions where you take one function and put it inside another. And to take the derivative of those kinds of functions, we need a new rule, and that is the chain rule. To use the chain rule, you have to look at a function and be able to see it in layers. You need to look at a function and understand what is the outside layer and what's the inside layer. So before we do any calculus, before we actually use the chain rule or even explain what it is, I want to take a moment to practice looking at a function and breaking it down into its parts, breaking it down into its layers. Looking at example 1, y equals x squared plus 1 squared, my goal is to take this function and break it down into layers where each layer is differentiable on its own. For example, when I look at this, I see that the outside layer is I've got something squared, and the inside layer is x squared plus 1. So I can rewrite this as a composition of functions where f of x is x squared, g of x is x squared plus 1, and f of g of x, where you take this function and plug it in right there, is x squared plus 1 squared. So the outside layer is something squared, and the something, the stuff that's being squared, is x squared plus 1. Example 2, looking at e to the sine x. I need to break this down into layers. The outside layer is e to some power, e to the stuff. And the stuff is sine x. Now, it doesn't sound very academic to say e to the stuff, but if you view it that way, if that's the way that you see it, it's going to make the chain rule much easier for you. Because now I can look at this and I can say my outside function, f of x, is e to the x. My inside function, g of x, is sine x. And when I create a composition of these functions, f of g of x is e to the sine x. Example 3, secant 2x. If this was secant x, no problem. The derivative of secant x is secant x times tangent x. I'm good to go. But it's not. It's secant 2x. So this is technically a function composition. I'm going to look at this as being secant of stuff, where the stuff is 2x. Okay? Secant of stuff, or secant of x, I can take the derivative of. 2x, I can take the derivative of. So I am breaking this down into layers. F of x is secant x. G of x is 2x, and f of g of x is secant 2x. Okay. Hopefully this is getting easier for you. You've got one more. Example 4, natural log of x cubed minus 4x squared plus 1. Again, how do I know that this is a chain rule problem? When I look at this and I think to myself, if that was natural log x, I could do that. But it's not. That is a hint that this function has layers and it needs to be broken down. So I've got the natural log of stuff, where the stuff is x cubed minus 4x squared plus 1. So f of x in this particular example would be natural log x. G of x is x cubed minus 4x squared plus 1. And the composition, f of g of x, is the natural log of x cubed minus 4x squared plus 1. So now that we've developed this skill of being able to take a function and identify its layers, we can take its derivative. Now we can understand what the chain rule really is. The chain rule says to take the derivative of a composition of functions, you're going to take the derivative of the outside layer. You're going to take the derivative of the outside layer and leave the inside alone. F prime of g of x. So you're going to, if you have stuff squared, the derivative of stuff squared is 2 times stuff. And then you're going to multiply that by the derivative of the inside. So you're going to take the derivative of the outside layer and then multiply by the derivative of the inside layer. And it's important when you take the derivative of the outside layer to leave the inside alone. And now that we have this practice, now that we can break functions into layers, we can actually take their derivative using the chain rule. Example 5, you'll notice examples 5, 6, 7, and 8 are the exact same problems we just looked at, so we already know how this breaks down into layers. F of x equals x squared plus 1 squared. And so I look at this and I want to identify the layers. The outside layer is stuff squared. So when I go to take the derivative, f prime of x, the derivative of stuff squared would be 2 times the stuff to the first power. Now, I don't really write the first power. Times the derivative of the stuff. So times the derivative of the inside function, which is 2x. And that's your derivative. Of course, we can clean it up, we can simplify, but that at its core is your correct answer. So this is 4x times x squared plus 1, giving me 4x cubed plus 4x. Example 6, g of x equals e to the sine x power. I know that my outside layer is e to the stuff. The derivative of e to the stuff is itself. So g prime of x is e to the sine x times the derivative of the inside function, which for this was sine x, so times cosine x, and there's really no simplifying to be done there. That's just our answer. Example 7, secant 2x. The derivative of secant x would be secant x times tangent x, so the derivative of secant 2x would be secant 2x times tangent 2x times the derivative of the inside function, which is 2x, so times 2. Example 8, to take the derivative of this function, the derivative of natural log of stuff is 1 over stuff. So the derivative is 1 over x cubed minus 4x squared plus 1 times the derivative of that inside function, which would be 3x squared minus 8x. Okay? And to clean it up and put it nicely, I can put that in the numerator. So I've got 3x squared minus 8x over x cubed minus 4x squared plus 1. Okay, in examples 9 and 10, I want you to pause the video and try and decide what are the layers of this function, and then unpause and see if you were right. Example 9, p of x equals sine of x squared plus 4. Okay, I look at this and I think if this was sine x, I could do that, but it's not. It's sine x plus 4. It's more complicated than that. So I'm thinking maybe this is a chain rule problem. Maybe this is a function that has layers. I want to break down the layers. So sure enough, when I look at this function, the outside layer is the sine of stuff. So the derivative of sine of stuff is cosine of stuff times the derivative of that inside layer, the derivative of the stuff, which is 2x. So I get my answer, 2x cosine of x squared plus 4. And number 10, I've got negative natural log of cosine x. That negative in front is just a coefficient. Remember, when you take a derivative, coefficients are along for the ride. So the derivative of natural log stuff would be 1 over stuff. So I've got negative 1 over cosine x times the derivative of cosine x, which is negative sine x. And I do want to simplify this. I've got sine x over cosine x, which is tangent x. So the derivative of negative natural log cosine x is tangent x. All right, 2012 AB number 7. If y equals x cubed minus cosine x to the 5th power, then y prime is what? So I look at this, I immediately see it's a function with layers. The outside layer is stuff to the 5th power, and then inside that I've got x cubed minus cosine x. So using the chain rule, the derivative is going to be 5 times the stuff to the 4th power, where that stuff was x cubed minus cosine x, times the derivative of that stuff, 3x squared plus sine x. Okay. Can I simplify this? Maybe, but it's good to stop and check. Does this match any of my answer choices? This seems to match answer choice E, so I am done. 2012 BC number 1, y equals sine cubed x. What is dy dx? Just a word of advice when you're taking derivatives like this, I like to rewrite the function like this, y equals sine x cubed. And the reason why I like to do that is because it makes it easier for me to see the layers here. When I write it this way, I can very easily see the outside layer is stuff cubed. So y prime, or dy dx, would be 3 times stuff squared, where stuff is sine x, times the derivative of sine x, which is cosine x. So if we were to clean that up, it would look like this, 3 sine squared x times cosine x. And that's answer choice E. Last one for today, and this one is foreshadowing what we're going to do in the next topic, which is functions that have more than 2 layers. Today we did the chain rule with functions that had 2 layers. This one has 3 layers. So if you want to pause the video, see if you can identify the 3 layers of this function, and then we'll take the derivative using the chain rule. Okay, so first I'm going to rewrite this function. Just like I did in the last problem, I'm going to write this as cosine of 4x cubed. And when I do it this way, I can see my three layers. My outside layer is something cubed. Inside that, I've got cosine of something. And inside that, I've got 4x. So since this function has three layers, the chain rule derivative is going to require three derivatives. To start off, I've got stuff cubed. The derivative of stuff cubed is 3 times stuff squared, where the stuff is cosine 4x. Times the derivative of cosine stuff. The derivative of cosine is negative sine, so times negative sine of 4x times the derivative of 4x, which is 4. Now, what I wrote here doesn't match any of my answer choices, but the cleanup process is fairly easy. 3 times negative 1 times 4 is negative 12. And really, you could stop right there. How many answer choices say negative 12? Only one, but I'm going to keep going. Negative 12 cosine squared of 4x times sine of 4x. And my answer choice is B. So to recap, if you want to take the derivative of a composition of functions, first you have to identify what your layers are. Your outside layer, your inside layer. Maybe if you have more than 2 layers, you would have a layer even further inside of that. And then you're going to take the derivative of the outside layer and then multiply by the derivative of the inside layer. And as silly as it sounds, as non-academic as it sounds to say the derivative of stuff squared is 2 times stuff to the first power, if you think about it like that, it really will make this easier for you. Because one of the hardest things about the chain rule is not doing the chain rule. It's remembering to do the chain rule. Identifying a problem where you need to do the chain rule in a context that's not taking notes over the chain rule. So it's important to get lots of good practice on this. And if you do, it's really, really, really going to help you down the road, especially in the next unit. So I hope that helps. Thanks for watching.